Okay, so here's where we were last time. We were talking about linear transformations, and here's our definition of a linear transformation. Right, we require the domain to be a vector space, the target to be a vector space, and for the function to satisfy this linearity property that we've actually talked about on several occasions in the past. Right, we've talked about linearity in different contexts. We are just finally, though, getting around to actually using it to define linear transformations. Okay, several different things to get said. Equivalent formulations, a little bit of terminology, math slang, I like to call it, and an example of how to actually prove that a function is a linear transformation. Brute force, you might say. So remember, you just have to show that putting a linear combination in gives you the appropriate linear combination out. Okay. Alrighty. So let's talk about some interesting linear transformations. Here's one. This is a linear transformation. Now, this used to bother me when I first saw this. It looks like what this is saying is, okay, this thing we're going to call capital D is the name of my linear transformation, and it's just, well, it's the derivative, right? If you note, our domain is collection of all differentiable functions, so take one of those differentiable functions and just take the derivative. So here's why it used to bother me, and this might be bothering you at this moment as well. I remember a lot of derivatives from Calc 1 class that weren't linear, right? Like sine x. Its derivative is cosine x, which is not linear. Okay, so the resolution of this concern is looking carefully at what we are defining as the linear transformation. The linear transformation is this thing, right? We are not claiming that the derivative is a linear transformation. Certainly not. What we are claiming is the act of differentiation is linear. Right? The derivative itself, oh yeah, it's a totally different thing. This function f prime, yeah, could be a cosine x, could be an exponential, or who knows, lots of different things it could be. These aren't necessarily linear, but the act of differentiation is linear. So that's the distinction, and make sure to keep that in mind. Here's the proof that this is a linear transformation. This is a linear transformation. Here you go. Let's put a linear combination in. Notice, into this alleged, candidate linear transformation, we're putting a linear combination of input functions. Our goal is to show that we get the appropriate linear combination out. So all we have to do is get from here to there. Doing so is a pretty straightforward process. Step 1, plug in. That's just straight from the definition. In this case, the next step is to recall a couple of facts about Calc 1, right? So we have a rule from Calc 1 that says that when you take the derivative of a sum of two functions, the result is the sum of the individual derivatives. That's old news Calc 1, right? Likewise, when you take a derivative of a constant times a function, well, then you can factor out the constant. You get a constant times that individual derivative. So Calc 1, you might say, gets us from there to there. And then, it's all over but the shouting, we just recognize that that is the definition of D of F1, and this is the definition of D of F2. And so, as required, linear combination in, linear combination out. So you can also see in this proof exactly what I'm talking about, claiming that, again, we're not saying derivatives are linear, we're saying the act of differentiation is linear. And you can see it right here, that this is the kind of linear combination we're talking about. Linear combinations of functions give you linear combinations of, by differentiation, gives you linear combinations of derivatives. We're not saying that linear combinations of, values of x that would go into these functions. That's not the same thing. That's not what we're talking about. Okay. Alrighty, so that's our first example. I'm going to show you a load of examples today. I'm not going to be able to go through and prove all of them, so most of these I'm going to leave as exercises for you to prove for yourselves. I am going to do a couple myself. Here's one, and this is an easy one to prove. You all will recall this function from chapter 1, right? Way back. We made the observation when we first started talking about determinants that if you have a matrix, you can interpret it as a function by way of this formula. Right? And I've been biting my tongue ever since, trying not to say linear transformation in reference to this function. I've been saying, the function that is defined by a matrix. Right? Well, what I would like for you all to prove here, as a true fact, is that any function defined by a matrix in this way is a linear transformation. All you have to do to prove this is show that if you put a linear combination of vectors in, plug into that formula, that what you get is the expected linear combination. So that's a nice exercise. Give it a try. You are going to use some previously established facts. Just like in this proof here, we used old facts about Calc 1. Right? Well, likewise, in doing this exercise, you're going to use old established facts about matrix multiplication. The algebra of matrix multiplication, or matrix algebra, as part of that process. So keep that in mind. Okay. All right. Here's another one. This is kind of a weird one, but I'm going to define a linear transformation called S. S is a linear transformation whose domain is C infinity. That's the collection of all, let's see what terminology we use. Smooth is a common choice here, but infinitely differentiable functions, F. That's our domain. So the inputs to this S are C infinity functions. The outputs are real numbers. And the formula for how you compute the corresponding output is compute that's integral. Right. So you might say that this linear transformation, this candidate that I'm proposing as a linear transformation, is the act of integration. Right? So you can interpret, my assertion that this is a linear transformation, you might casually interpret as saying integration is linear. Okay. Again, interpreting appropriately, interpreting integration as something you do to a function to result in a number. Okay. Not talking about anti-differentiation. A totally separate thing. Okay. All right, here's another one. This next one I'm going to prove for you. You might call this next one weighted integration. So the idea is, again, here's my linear transformation, my candidate linear transformation called SG. SG takes as its input a C infinity function, and it gives as its output a real number. Here's the formula for that output value. Notice that this makes reference to F, right? So you can see how F is involved in this calculation of S of F. It also makes reference to this function called G. G, this thing here, has to be set and fixed. That is part of our function, S sub G. So, give me a G, I will make from that G this function called S of G. And S of G acts on functions like F, like so. Okay. So let's prove that this is a linear transformation. Note I didn't prove example number 3. I'm going to leave that as an exercise for you guys. It's going to be very, very similar to what we're about to do here, but I will show you now explicitly how to prove that this SG, defined by this formula, is linear. All right, here we go. Come up here. Let's see here. Why don't I go over here to the right? Let me zoom way in so I can give myself some space. Okay, so I need to show that SG that if I put a linear combination into here, I need to show that what I get is the corresponding linear combination out. Okay, so specifically, I need to look at C1F1 plus C2F2 as my input, and I need to show that I get the expected linear combination as my output. Okay, so first thing I'm going to do, write down straight from the definition, what is this SG? SG says take integral from A to B of that function times G dx. Right, that's straight out definition of what that thing SG is. Okay, now a little bit of algebra. I can distribute the multiplication there. Right, I can rewrite this as C1F1G plus C2F2G. Yeah? Everybody happy? That's just algebra. Okay, next, old fact from Calc 1. If you have an integral of a sum of two functions, you can rewrite that as the sum of two separate integrals. So I'm going to rewrite this as integral from A to B C1F1G dx plus integral A to B, C2F2G dx. Now again, that's just Calc 1, old news. Right? Here's some more Calc 1 that I know y'all all remember. Constants factor outside of integrals. Right? So I can send those constants right to the outside, and here we get integral from A to B. Oh, excuse me, forgot to factor out my C1. C1 integral from A to B F1 times G dx plus C2 integral from A to B F2 G dx. Is everybody happy so far? Cited a couple of facts from algebra, a couple of facts from Calc 1, just rewriting the expression that I started with, gotten down to here, and then lo and behold, these things are familiar. This thing here is the definition of SG of F1. And this thing here is the definition of SG of F2. And so, as required, right, as we were hoping would be true, okay, one more zoom out. As we were hoping would be true, if I put a linear combination in to this SG function, I get the expected linear combination out of this function. So SG satisfies the linearity property. How are we doing? Everybody on board? Everybody follow the process there? I mean, the way, the direct confirmation that something is a linear transformation, put a linear combination in from the domain, do what you can do to manipulate it around as necessary to show that you get the expected linear combination out in the target. Okay. Alrighty. Okay. So that confirms that is a linear transformation. Okay, so keep in mind, I skipped this one. I'm going to let y'all do that as an exercise. It's going to be a lot like what we just wrote down for the for item number 4 here, and make sure to give that a try. There's a few others. This next one, gosh, I really wish I had time to talk about all this stuff down here. There's some really fun, wacky stuff in there. If anyone's curious, if anyone wants a preview of what I think they're going to mention in Math 353, come to office hours. I'd love to talk about this. It's really interesting. But what I'm going to do here is just observe that this is, in fact, a linear transformation. C infinity function goes in. Here, let me color code as usual. This thing is a linear transformation. It takes a C infinity function as its input. So this f here, you give me any smooth function. The output value of this linear transformation is just f of 0. You might call this the plug-in 0 linear transformation. So the act of plugging in 0 into functions. It is a linear transformation. Now, this is something y'all are going to prove, and just like all the other proofs, suppose you plug in 0 into a linear combination of functions. Confirm that you just get the corresponding expected linear combination of what you would have gotten if you'd plugged in 0 into the functions individually. Okay, so easy proof, just a matter of following the rules and following the process. So here's a variation. This says we're not going to plug in 0. Here we're going to plug in something other than 0. Here we're plugging in some other number A. I think you can probably persuade yourselves there's nothing magical about 0 when it comes to plugging into a function, right? This is just as good. But notice, furthermore, we're also taking several derivatives first. Well, as we've previously discussed, the act of differentiation, we've already seen. That is a linear transformation. So everything that we're doing here is all linear. So this too is a linear transformation. Again, a great practice proof. Think about if this were an exam question, how would you write that down? Good practice problem. Okay, flashback. One of the instances where we used the word linear previously was at the start of chapter 4. We started talking about what we wanted to call linear differential equations, right? And we defined these linear differential operators, we called them. L. Y'all remember the whole L thing. L is the process of computing the left side of a differential equation. Right? And we proved at the start of chapter 4 that process was linear as we described it at the time. Now, so all I'm doing here is same statement, nothing really new mathematically. Here I just want to point out that, okay, now that we have developed the terminology, all that was showing is that this L is a linear transformation. So linear differential operators from chapter 4 are linear transformations. The proof is the same as the proof that we did back in chapter 4. So one thing you might do just to entertain, a practice problem for your own curiosity, don't flip back to chapter 4 right away. Try this as a practice problem on your own first, and then having written down what you think is a reasonable whack at it, then flip back to chapter 4 and look at the proof there. Okay. All right. Okay. So that's a bunch of examples. We're going to see some more examples as we go along here, but we do have to make some observations about linear transformations, a couple of definitions, nice application at the end. First theorem that we're going to observe, if you know about a basis in the domain, to keep in mind, a domain's a vector space. Okay, so suppose you have a basis for your domain. Remember what a basis is. It's a set of vectors in the domain. It's independent and that spans. Okay. If you have a basis for the domain, if you know what the linear transformation does to a basis, the word image here means, what comes out when you apply the linear transformation. If you know the images for a basis, then I claim that you actually know everything that there is to know about that linear transformation. This is a really surprising fact the first time you see it. This suggests that even though this vector space V has infinitely many vectors in it, that's a lot, right? Even though it's got infinitely many vectors, if you tell me the value of t just at a handful, then I can automatically tell you all the rest. This seems like an outrageous suggestion. So let me prove this fact for you. Here we go. So keep in mind we've got a basis for the domain. these vectors v1 through vk. Reminder from chapter 2, if you have a basis for the domain, every vector in the vector space can be viewed as a linear combination of those basis vectors with some choice of coefficients. Reminder, while we're here, these coefficients, right, our assertion here is that these are uniquely determined. So for every vector, there's exactly one set of corresponding coefficients. These are called the coordinates. So I hope you all remember that from it was a long time ago, back in chapter 2. But those numbers that you need to use as coefficients in a linear combination, those are the coordinates of that vector. Okay, so we had a basis, so we know we can do this, and I'm going to then write down what happens when you apply t to that vector. Well, there it is. Right, v, as noted above, is that linear combination. We apply the linearity. T is a linear transformation, which means if you put a linear combination in, as I just did, then you get the expected linear combination out, like this. And we are now actually done. Right? This formula tells us that we're done. Let me walk you through why it does. Keep in mind, the premise of this question is, suppose you know the images of a basis. So by assumption, I know T of V1 through T of VK. I know all those. Right? Well, then, simply by virtue of knowing what vector we're talking about, namely by knowing its coefficients, if I know those, then I know everything in this formula for T of V. Right? So at this point, you give me any vector v, whatever vector, I don't care, any vector at all, I can find those coordinates, C1 through CK, plug into this formula in which I know these images, and I can therefore compute T of that vector v. Always works. It's a really nice result. So again, a little bit surprising to suggest that simply knowing what the linear transformation does to a handful of vectors in the domain, just a handful, is enough to tell you all of the infinitely many values of the function. The way I like to see this is this communicates how strong of a condition linearity is. Right? Linearity is what makes this work. And linearity, therefore, is so powerful of a condition that it lets you extrapolate from just a handful of values the entire rest of the function. That's one way to look at it. Okay, quick example, get our hands dirty. Here is a couple of vectors in the domain R2. We've got some linear transformation from R2 to R3. Notice that these are a basis. Right? So simply by knowing those images, just those two images, I can tell you the value of t at any other vector. And for example, how am I gonna find t of 3, 4? Well, 3, 4 is a linear combination of these basis vectors. Now, there's some side linear algebra that you've got to do. You've got to, figure out what are these coefficients. In this case, 3, 4 is, well, it's the coordinates are 2 and 1. Said differently, the 2, 1 linear combination of these given basis vectors. But as soon as I identify those coordinates, then I just say the magic word linearity. Right? Cite that I am given that value, and I'm given this value. We already know these coordinates are 2 and 1. And we're good. T of 3, 4 then is just arithmetic at that point. It was always going to work. Okay. Alrighty. Okay, another definition. Got to define something called the kernel of a linear transformation. It's a pretty familiar idea. Here's the notation to describe kernel. Let me just walk you through this, what this is saying. This says the kernel of a linear transformation, T, is the set of vectors in the domain that have the property that the linear transformation sends those vectors to 0. Right? That's what that notation means. It's translating into English. I say this is a familiar concept. We've seen this kind of thing before. Notice, for example, if you have a matrix, if you think of a matrix as a function, the kernel of that matrix is, this familiar old concept of null space. Right? Let's look at, if I need T of V to equal to 0, that means I need this to equal to 0. That means I need AX equal to 0. What X's have AX equal to 0? That's the definition of the null space. Right? So, like I say, pretty familiar concept, at which point students wonder, well, what's the difference? How come kernel isn't just exactly the same as null space? And it's a very slight difference, really. It's just an application. The word null space just applies just to matrices. Right? The word kernel applies to any linear transformation. Now, here in this example, we chose to look at a linear transformation that happened to be a matrix. Right? So in this case, they are the same thing. But the word kernel can apply much more broadly to linear transformations that might not be matrices. And sometimes that happens. Okay, so a hands dirty example. Let's look at this one here. There's a linear transformation. I know it is because it's a matrix times the input vector. You guys have already gotten a practice problem suggestion for me to prove that those are always linear transformations. Okay. Notice that what this does, this could be rewritten as T of X equals AX. Right? And we can then compute out and find that it just gives you X comma Y comma 0. Right? So let's see here. Let me write this a little bit differently then. So T of XYZ is XY0. That's, if you multiply out that matrix, that's what this linear transformation does. So geometrically, you might think of it as that this linear transformation shoves points wherever they might happen to be, projects them down or up, but shoves points into the XY plane. Projection into the XY plane. Okay, so my assertion is that that's a linear transformation. With that in mind, let's ask the question, what is the kernel? The kernel, recall, is a collection of vectors in the domain that hit 0 when you apply the linear transformation. So, looking back at this picture, what vectors are they that when you project to the XY plane, you hit the origin? And I don't think it takes too much persuasion that it's the z-axis. So the kernel of this linear transformation is the z-axis. Okay, everybody happy? Alrighty. Okay, here's another example. Let's suppose we consider our usual, chapter 4 style linear differential operator, L, right? What is the kernel of that as a linear transformation? Well, again, kernel means the collection of things that when you put into the transformation out comes 0. So the kernel is the set of functions that give L of y equals 0. In other words, it's the set of solutions to the homogeneous equation. So another familiar thing, right? We've already talked about solutions to a homogeneous differential equation. We didn't have the terminology at the time, but now that we do, we can say that what we were looking for when we were finding solutions to the homogeneous differential equation, what we were looking for was a kernel of a linear transformation. Okay. All right, so just rehashing an old idea, saying it in new language. Okay. All right, here's another definition, another important definition relating to linear transformations, something called the image. The image is, well, we've talked about this already. It's the collection of all the actual outputs. Remember, we distinguish between the image versus the target. The target is the space that outputs have to land in. The image is the actual outputs, the collection of actual outputs that actually do come out. So note that here in the definition. The image is a set of vectors in the domain, vectors in the target, such that that target vector is an output from a vector V that's actually in the domain. Right, so it's a collection of actual outputs. Again, just sort of translating the language of this notation. Okay. So I claim this too is something familiar when it relates to matrices, and it's a little bit more effort to see this, how this comes about than the null space argument was a fairly easy one. But let's consider this here. What is the image when you're looking at one of these matrix linear transformations, right? So we've got a matrix given, let's say that one, given a matrix, define it as a linear transformation in the usual chapter 1 way. What is the image? Okay, well, no big deal. The image is the collection of all possible of these. It's the collection of all possible outputs. Okay, well, outputs are AX. Reminder from way back. Here's how you multiply a matrix times a vector, right? We take linear combinations of the columns where you use the vector that you're multiplying by as your coefficients. Okay, so again, reminder from chapter 1. So what this is saying then, the collection of all possible outputs, the collection of all possible products, is the collection of all possible linear combinations of the column vectors. And you got to ask yourself then, what does that remind you of, this terminology, the collection of all possible linear combinations of the columns of a matrix? Well, again, that's a familiar old thing. That's the column space. Right, so I made a sort of a dangling assertion way back when we were in section 2.4, I guess it was, when we were talking about row space, null space, column space, that we would have a future natural interpretation of column space. Didn't have the tools to talk about what that was at that time, but here it is. This is the natural way to think about the column space. The fact that it's linear combinations of column vectors, okay, whatever. The more important fact about the column space is that is the image of that matrix thought of as a linear transformation, which of course we often do. Okay, looking at the function on the previous page, let's see here. Here was our function on the previous page. Remember, this function acts to project into the xy plane, right? The image, therefore, is the xy plane. No surprise there, right? I mean, what comes out of this process of projecting into the xy plane? Well, the entire xy plane. So note then, as we just asserted, this xy plane, that image, that xy plane, actually is the column space. This is the span of the column vectors. The column vectors of the matrix on the previous page being these, right? So, 1, 0, 0, 0, 1, 0. That's these two vectors. The third vector is the 0 vector. That doesn't contribute anything to the span. So the span of these two vectors, the column space of the matrix, in other words, you can directly see is the image of the linear transformation. Okay, maybe let me hit the pause button for a second here. Does anybody have any questions? I'll breathe while y'all decide if you want to ask a question. Anybody? Yes.
Simple question. First one was you said that the kernel is equal to 0 for
Where are you? I'm sorry.
For the kernel to use the z-axis.
Yeah.
Can you just express that as a kernel of 0, 0, 1?
Well, so the kernel is the entire z-axis, and that's a vector space. If you want to say that a basis for the kernel is 0, 0, 1, absolutely. Sure. But you always want to make sure to distinguish between the vector space and a basis for the vector space, because they are importantly different things. Yeah. They're very closely connected, and one is very, very useful in understanding the other, but they're different things.
Okay.
Yep.
So if I gave you the basis and said this is the basis of the vector space, would that give you an answer?
It depends on the phrasing of the question. It could be, but it depends on how it's phrased. Yeah. Right. Okay. So I can't give you a complete answer because it's question dependent. Yeah. Okay. A couple of exercises. A couple more exercises. These are kind of mashup exercises. So first exercise, I want you to prove that with any linear transformation T, the kernel of that linear transformation is always a subspace of the domain. So here's why I call that a mashup. I mean, obviously this involves ideas from here in section 5.1, but it also involves ideas from way back when in section 2.2 on subspaces. So you got to think to yourself, wait a minute, how do you prove something's a subspace again? There was a process. There's a little trick to it. So you got to think about that, and then think about how that applies to this scenario where we're looking at a kernel. So there's a nice exercise combining ideas from different contexts. So I have something to think about. Second exercise: prove that images are always subspaces of the target. Likewise. How do you prove something is a subspace? How is that relevant in this case? And how do you actually write that down? Okay. All right. So these would be great questions to ask in discussion section or office hours or to a group of study partners, something like that. Give it a try on your own first, but if you have trouble, good topic of discussion. Okay. So here's this is a really surprising fact about linear transformations. If you have a linear transformation, and then an important little caveat, if the domain is a finite dimensional vector space, we have to put that in there, otherwise this doesn't really make any sense. But so if the domain is a finite dimensional vector space, and you have a linear transformation T, here's a remarkable fact. The kernel that we know sits inside of the domain, and so the kernel lives over here. The image, which of course lives inside of the target, the dimensions of those subspaces relate to each other. I find that right off the bat surprising. Look at this, they live in different worlds. Right? This one lives in V. That one lives in W. They're completely different vector spaces. A little surprising that their dimensions relate. Specifically, the dimension of the one plus the dimension of the other, the sum gives you the dimension of the entire domain. Really weird fact, but true. Okay, I'm going to show you a couple different ways to prove this. Well, I'm going to refer to a couple of different ways to prove this. The first way that you can prove this is look and see how the book did it. I think how the book did it was kind of rough, kind of tedious. I don't think you're going to like it. But go ahead. Feel free if you'd like. I'm going to show you a different way to prove it. Now, my way of proving this is I'm not going to be able to finish the proof today because we don't quite have the tools. But mine's ultimately, in the big scheme of things, going to be a lot easier. So I'm going to leave one asterisk that we'll have to fill in a few days. And at that time, we'll fill in that one last little asterisk, and the proof will be complete. So the asterisk is what I'm not going to be able to prove today. That when you have a linear transformation defined on a finite dimensional domain, it can be written as a matrix. Now, there's a bunch of stuff that goes into showing that this is true. But it's a true fact that we're going to have proved in less than a week. Okay. All right. So for the moment, let's take this on faith, or if you like, we can think if you prefer, we're only going to prove the above theorem for the moment in the case of linear transformation that can be written as matrices. Okay. All right. So, hey, here's the good news. If with that established, we already know kernels are null spaces if you're talking about a matrix, and images are column spaces if you're talking about a matrix. So, in fact, then, this brand new assertion that we're making about the dimension of a kernel, dimension of an image, in this case that you're talking about matrices, really all that's saying is this old fact that we've already proved back in chapter 2. And that is, remember we went to a bunch of trouble, figured out how to find a basis for a null space, how to find a basis for a column space. This one involves finding columns that don't have pivots. This one involves finding columns that do have pivots. The grand total, you get the total number of pivots, or total number of columns in the matrix, in the special case that we're talking about matrices, we already know this is true. It's the same statement as this old fact here. Okay, so I like that much better. I find this a much more satisfying argument. And now, again, I do owe you a demonstration that linear transformations on finite dimensional domains can be thought of as matrices. And we will circle back on that. Okay, a nice corollary. Before I get to the corollary, let me address some terminology. My experience tells me that y'all have probably forgotten what these words mean, or perhaps might never have seen them. In theory, you have to talk about these ideas in a Calc 1 class, because if you want to talk about, what does it mean for a function to be invertible, you have to talk about what it means for a function to be one-to-one and what it means for a function to be onto. For example, if you want to talk about the, how do you take the derivative of arcsine? Well, arcsine is an inverse function. And if you want to make a reasonable definition of it, you have to define what does it mean for a function to be invertible. So anyway, all of this should have been in a Calc 1 class, but I know that very often Calc 1 classes kind of gloss over this. So let me define for you what it means for a function to be one-to-one, what it means to be onto. Keep in mind, a function has a domain. Let me make it taller and skinnier. I'm going to symbolically represent the domain as just a collection of points like this. This is just for symbolic convenience. And here's a possible target. Again, I'm just going to make a collection of points. Here is some function f. Okay, and maybe the function does the following. Maybe the function sends this point to there, and this point to there, and this point to there, let's say. Right, but it might do something different. It might send this point also to there and this point to there. Who knows? Okay. For each one of the points in the target, you can define something called the pre-image. So here, this point here, the pre-image is the collection of points in the domain whose image is that point. Right, so it's kind of like what do you get when you back trace through the function? Okay, so what it means for a function to be one-to-one is that every point has at most one pre-image. And what it means for a function to be onto is that every point in the target has at least one pre-image. All right, so the function that I have described right here that I've drawn a picture of, this function is not one-to-one because this point here has two pre-images and that's not allowed. So this function is not one-to-one. Okay. This function is also not onto, because this point does not have at least one preimage, right? To be onto, you need to have at least one preimage. So this function is neither one-to-one nor onto, and so this function's not invertible. And you can consider different variations of this. So, for example, what if the function does this? Is this function one-to-one? Well, this point has exactly one preimage, that point has exactly one preimage, that point has exactly one preimage, and so this function is both one-to-one and onto, and thus invertible, yeah.
So you said onto just requires every point to have at least one preimage?
At least one.
So if it has more than one.
Totally cool. Yeah.
But it's not one-to-one.
Correct. That's right. Yeah. So one-to-one means at most one preimage. Onto means at least one preimage. So both one-to-one and onto means exactly one preimage. Yeah. Right. Okay. So this is what we're talking about when we say the word bijective. Every point in the target has exactly one preimage. That's just terminology. Again, one-to-one and onto both together at the same time means exactly the same thing. All right. Now, how does this play into our theorem? We've got a theorem here that says if you have a linear transformation here from V to W, if it is bijective, then the domain and the target have the same dimension. And that's pretty surprising, right? Because again, these are different vector spaces, and why would they have to have anything to do with each other? Okay, it turns out this is actually an easy one to prove. Let me draw a picture of such a linear transformation. Here's our V, and here's our W. Every point has exactly one preimage. 0, therefore, 0 has exactly one preimage, and that is just 0. Right? That's exactly one preimage. Furthermore, every other point has exactly one preimage. Every other point. Exactly one preimage. So let's think through in a scenario like this where you have a bijective linear transformation. What's the null space? The null space, the kernel. What is the kernel of this linear transformation? What are the vectors that hit 0 in the target? Well, it's bijective, so it's just this one lonely little 0 vector by itself. And the 0 vector by itself is 0-dimensional. So in this case, the dimension of the kernel is 0. What else can we say in this scenario? What is the image in this case? We have, again, a bijective linear transformation. What is the image? How many points over here in W have at least one preimage? Well, all of them, right? By assumption, these points all have exactly one preimage, and therefore they all have at least one preimage. Therefore, every point in W is an actual output. Therefore, W is the image. It's both the target and the image in this case. And so that means that the image is W, and therefore the dimension of W is equal to the dimension of V. So this is an immediate consequence of our sort of, revamped rank nullity theorem. Dimension of V is equal to dimension of W. Okay. All right, so this makes for a pretty good stopping point. We'll call it a day here. Y'all have a nice day. See you on Friday.